Hello everyone, I'm Hao Huang and today I will introduce something about the GLM for my Module 3 presentation. So let's start with our data. So this is a data uh, in a fitness program that's about 30 participants, how their um, body features, and I will do some analyze with them and I will use GLM. So what is GLM? GLM is the general linear model that's nothing more than this formula y equals bx plus epsilon. So this model is a line model that shows the linear relationship between outcome and predictors. And y is the outcome, what we usually call dependent variable in experiments. And b is the weight of those predictors. And x is the predictors. It can be a matrix of several predictors. And epsilon is the residual of the model, or it can also be regarded as errors in some different philosophy thoughts. Well, and there are many methods based on GLM, and today I will introduce two of them. One is regression. I will do multiple linear regression later, and another is ANOVA and list of variance. Okay, and now I will start to introduce regression. So what is regression? Regression is a way that we try to use a line that has the least square deviation when describing data. There are some assumption of regression. One part is the relationship, or absolutely for the GLM, we can only describe the linear relationship. And also we need to make sure that the predictors and the outcomes are logical. And another part is about residual or errors. This is the most important part for the regression or even in the GLM. So that's why because Gauss-Markov theorem talks about this. Only we miss these assumptions of errors can we get the best linear unbiased estimate. So I will do it in the later diagnostic parts. Now, just try to start our regression analyze here. Here I use the amount of breakfast they eat and the amount of fruits they eat to predict the increasing weight in this program. And I run this code in R, and it talks about some residuals, and this is the important part we need to know. It talks about the weight of those effects. The now the effect of breakfast is 0.5, and the point of fruits about minus 0.05, and interaction effects around 0.3. And we do the hypothesis test here and seeing the effect of breakfast and the effect of interactions are significant, while the fruits effects are not significant. Okay, and because the interaction effects are significant, so I run another regression here to ignore the interaction effects to make sure the main effects of the breakfast is happened, and we can find it has higher residuals, higher standard errors, which means with better contains the interaction effect here, which can better describe the relationship, and those estimates are the weight of those effects, and it seems there are some numbers that we can compare, but actually we cannot do comparison of these weights. It's a easy taken mistakes that Gary King has taught in 1985. In fact, those estimates cannot be compared because they just tells they can influence the outcomes, but they cannot be compared each other. Somebody may ask, why not use the standardization uh, better, which seems should be compared. No, no, standardization doesn't bring us more information. So just know that it tells us something and it cannot be compared. Okay, and I will do some diagnostic here. And the first is about the collinearity. Collinearity is not such a big problem if only, but it helps us only if you find some abnormal results. For example, if some uh, we get a better higher than one, that's impossible because due to the definition of the beta, it should be between -1 to 1. So maybe the collinearity happens uh, here because as the Cortiner says in 2002, the collinearity, uh, which means the some uh, predictors has some are dependent. So we cannot uh, constant other predictors to only increase one predictor. That's caused the abnormal results in beta. So in this situation, I don't have a abnormal beta, so I don't, and this variance inflation factors, which shows the which shows the how much the variance of the estimated regression coefficient is increased because of collinearity. So they are just around 1, so they are not so high. Maybe they are not a problem. And second diagnostic, I read in the plot here. It's about the independence of residuals is one of our assumption. And we want a straight line in the middle, but this line seems, because it's sensitive to observation, it seems not so perfect. It may be a little problems here. And we can also see the normality of residuals because we need a normal distribution of the residuals, but it seems number 14 or number 26, those observations seems a problems to fits the normal distribution. So there may be some problem, maybe bring some problems. And of course, I watched the homoscedasticity of my regression, and I also want a straight red line in the middle. It also be sensitive to the observations. So it's not so perfect enough, but it seems close to be the middle. And the last two diagnostic, I watched the outliner influence. So in this plot, I can see some Coke's distance there. If an observation is out of this line, that means they can influence the models a lot. So they may be a potential outliner. We should think about if we accept these observations. But this in these examples, fortunately, we don't have. So I make a conclusion for the MRC here. So I think the breakfast affects people's increasing weight significantly, and the interaction effects of the fruits and breakfast still helps to increase their weights. Um, and we check the regression and think the effect of collinearity is not so high, but still may be little problems about independence of residuals and the normality of residuals, distribution of residuals. And also it has slight evidence for heteroscedasticity, but we don't have evidence about a powerful outliner. So that's a good beginning for my research. And then the second part, I want to use ANOVA. ANOVA is another method based on GLM. That's why they have the similar assumption. called IID, independent errors, identically distributed errors, and distribution of errors is normal. But that's not means, uh, um, here I use the ANOVA to analyze some nominal variables. We compares different groups' contributions to the outcomes. But that's not doesn't mean we can only use ANOVA to analyze those kinds of data. In fact, um, the regression is a more general model than ANOVA. It incorporates many types of ANOVA in one statistic model. As the Gary King says in 1985, even many ANOVA computer programs do regression analysis and then transform the results into ANOVA parameters for presentation. They are both based on GLM, so they have the same um, some theory behind this method. So, but now I just want to use ANOVA here, and when I type the code in our program, it tells me the warning about the data is unbalanced. That's one problems when using ANOVA, because we have strict assumptions. We need a balanced predict data here, but well, so it's not a good start. And I want to look for the homogeneity of error variance, and the box plot seems tell us the variance doesn't um, equivalent. But so we run the Leibniz test, but the hypothesis test tells us we cannot reject the null, so we cannot think they are different. Well, the variants are different. Well, and the other four diagnosed are the same as I have done in MRC, and it seems we have a better result, much more better results than before. So, and do another conclusion for my ANOVA results is, unfortunately, I have no significant predictors. Oh, I haven't taught that before, because the p-value here for those three effects are higher than 0.05. So, oh, I don't like ANOVA. And the plot seems not satisfies the homogeneity, but the hypothesis test doesn't reject null. Maybe there's is a problem, but the hypothesis test doesn't think it's a problem. And the underdiagnosed of this ANOVA seems no problems there. So maybe the predictors I choose, the gender, the pills, doesn't have effects for the weight increasing. So I need to find other predictors that can predict the outcomes. Yeah, and I don't like ANOVA here because I have a more strict assumptions, and it even don't give us a linear model. We can just know they are if they have some effects. But in the regression, we have those estimates here, and we can write a formula that's right. We can draw a line that fits the model. So, and as some other researchers has said, regression is a more general model than ANOVA. So, if you have such kinds of data, maybe choose the regression is a better idea to analyze those data. That's all my presentation for Module 3. Thank you very much.